We challenge the very foundation we stand on, the comforting warmth in the atmosphere, and the seemingly unchanging landscape beyond our windows. Our daily existence rests on a fundamental belief that Earth is a temperate, welcoming, verdant world. We take for granted the enduring polar ice caps as remote, unchanging white crowns atop a blue sphere. We regard the current climate, the one that nurtured our urban sprawl, agriculture, and societal progress, as the standard norm. Yet this perception deceives. The environment we inhabit now defies the typical pattern. It's an uncommon, temporary, and delicate anomaly. Step back from the immediate view and consider the past million years, compressed into one expansive chronicle. You'd uncover a starkly altered truth. Our world isn't characterized by mild temperatures but by unrelenting chill. Across most of humanity's timeline, Earth has endured as a frigid, snowbound, unforgiving realm. Glacial expanses didn't limit themselves to the poles. They advanced like colossal forces over land masses, entombing North America, Europe, and Asia beneath towering ice walls reaching 3 kilometers in height. The glacial epoch hasn't ended. It's just dormant. The ice masses haven't disappeared. They've withdrawn, retreating into the fringes of the Arctic and Antarctic, poised for the cue to advance once more. We're attuned to that cue this evening, seeking an underlying cadence, a concealed sequence that shapes our planet's destiny. This rhythm unfolds on timescales beyond a single lifespan, invisible to us, yet its force commands the ebb and flow of seas. Approximately every 100,000 years, in a deliberate celestial pulse, the globe ices over and thaws with equal predictability. Such is the enigma of the Milankovitch cycles, revealing how our world's understated orbital ballet amid the cosmos determines the survival of all surface life. It's a tale woven from calculations, orbital dynamics, and the ingenuity of an isolated captive who unraveled the secrets of glaciation amid the flames of global conflict. We'll explore the mechanisms of this immense astronomical timepiece. We'll confront the glacial barriers that subjugated entire landforms. We'll gaze upward and grasp how a minor axial lean or subtle rotational sway can transform fertile lands into barren deserts. To uncover the pulse of antiquity, we venture to Earth's most silent expanse, the heart of the Antarctic Plateau. At the Russian station, Vostok, temperatures plummet to -89 degrees Celsius, a realm so frigid that exhaled breath solidifies mid-air and drifts down as crystalline frost. It stretches as an endless, monotonous white expanse, identical in all directions. Yet Vostok's real significance isn't its surface barrenness but the secrets buried below. Beneath the researchers' footwear sprawls an ice layer almost 4 kilometers deep. Far from uniform, this ice serves as an archive. Antarctic snowfall persists without melting, accumulating in successive strata season by season. Fresh layers compress the older ones underneath through sheer pressure, densifying the loose flakes into dense, azure-tinted ice. In this metamorphosis, vital elements get preserved. As snow crystallizes into ice, it encases minute air voids amid the structure. Once frozen solid, these voids lock away permanently, forming infinitesimal historical vaults. Each holds a snapshot of the atmosphere from the precise instant the snow descended. Drilling 100 meters deep yields air from the Roman Empire era. At 1 kilometer, its atmosphere predating any human societies. And at Vostok, they've penetrated even further. Over years of grueling toil that pushed human resilience to its brink, scientific teams sank a borehole into the ice sheet's core. They extracted lengthy ice cores, cylinders exceeding 3,000 meters. Examined in a lab, these appear as sleek, translucent rods akin to glass. But peer nearer, and you'll spot them. Countless, minuscule, entrapped bubbles. These are the planet's petrified exhalations, harboring carbon dioxide, methane, and particulates from bygone eras. By pulverizing these specimens in a sealed chamber and examining the released gases, we sample the breath of distant history. The Vostok core extended our view back 400,000 years into the past. Subsequent samples, such as those extracted from Dome C, pushed that timeline to 800,000 years. This archive stands as the fullest, unbroken, and finely detailed chronicle of climatic shifts ever unearthed. It's essentially a frozen pillar of time, shielded from decay and wear, ready for us to decipher its secrets. Once the scientists arranged the findings from these ice samples and charted the patterns of temperature and CO2 concentrations across almost 1 million years, the results weren't a flat trend or utter disorder. Instead, they revealed a pulsing rhythm. The Vostok evidence left no room for doubt. It was strikingly precise. Graphing Earth's temperatures over the past 800,000 years produced a line that didn't meander without purpose or mimic the erratic swings of daily weather. Rather, it resembled the operation of a precise mechanism. The plot created an ideal recurring zigzag pattern known as the sawtooth. Picture the jagged edges of a saw. One flank stretches out gently over time, while the other drops sharply. That extended, steady incline signifies the onset of cooling. Over about 90,000 years, our planet cools progressively and unyieldingly. Ice caps expand steadily, year after year, overtaking vast land masses. Worldwide temperatures plunge toward the peak of an ice age. Then comes the abrupt shift, the sheer vertical drop of the pattern. In what amounts to a mere instant on geological scales, maybe just 10,000 years, warmth surges back. Glaciers retreat dramatically. Seas rise and inundate shores. The environment flips from intense cold to a mild, balanced interglacial phase, much like our current era. Right away, the gradual descent toward chill resumes. This cycle unfolds repeatedly, occurring 8 times within the last 800,000 years. Roughly every 100,000 years, Earth draws in the frost before releasing a short burst of heat. The cadence is as reliable as a ticking clock. It's the planet's vital pulse. This revelation transformed our understanding completely. It showed that ice ages weren't flukes born from chance events like volcanic blasts or wandering space rocks. They followed a predictable loop. They were bound to happen. An underlying force orchestrated this regularity, potent enough to encase the globe in ice, yet so exact that it adhered to a timetable as dependable as time itself. Yet this driving beat didn't originate here on our world. No 100,000-year pattern hides in shifting crustal plates or swirling sea flows. Earth is a realm of wild unpredictability. It doesn't mark time with such fidelity. To uncover the architect behind it, we needed to gaze beyond our planet altogether. We awaited a Serbian mathematician confined in a jail cell and observing a flickering candle flame to grasp that the key resided in the flawless celestial arithmetic overhead. The solution to the Ice Age puzzle didn't emerge from a field expert atop an icy summit. It arose from that same mathematician in captivity. The year was 1914, with global affairs spiraling into the turmoil of World War I. As forces assembled and great powers collapsed, a Serbian engineer and mathematician called Milutin Milankovic faced arrest by Austro-Hungarian officials. branded an enemy foreigner. He was pulled from his newlywed bliss and ultimately held in Budapest. Amid the external world's destruction through shells and poison clouds, Milankovitch achieved something remarkable. He ignored the turmoil of the moment and delved into the quiet annals of history. He received a minor concession, permission to access the Hungarian Academy of Sciences library. There, day by day as Europe raged in flames, he labored solely with a pen, reams of paper, and a calculating slide rule. He undertook a challenge that still feels nearly unattainable. He resolved to model Earth's climate across the preceding 600,000 years. Ice cores were unavailable to him, nor were advanced computers. He lacked the modern geological records we rely on now. All he possessed were fundamental physical principles. Milankovitch was convinced that planetary weather wasn't haphazard. He saw it as a system powered by solar radiation. If it operated like machinery, then its dynamics could be computed. His logic was that by pinpointing Earth's precise orbital stance relative to the Sun throughout ancient eras, he could quantify the sunlight striking various latitudes at any moment. The math involved immense intricacy. It required factoring in the tugs from Jupiter and Saturn's gravity, Earth's own redistributing weight, and the intricate dances across the whole solar setup. He toiled alone for years, covering countless sheets with intricate hand-scrawled trig formulas. In his mind, Milankovitch extracted the planet from its orbital path and rotated it in reverse across the ages. He was building a spectral model of the world through mathematics. As the calculations started to converge and the notebooks brimmed with data, an underlying rhythm surfaced amid the script. This wasn't random scribbling, it formed a cycle. Milankovitch grasped that our world doesn't navigate an empty expanse. Instead, it navigates a network of unseen influences. These gravitational pulls from far-off colossal bodies were gradually and steadily reshaping the planet's trajectory. He had uncovered the mechanisms driving the vast astronomical timepiece. Prior to Milankovitch, the field of geology largely focused on downward examination. When researchers pondered the reasons behind climatic shifts, they sought explanations in sediments. They examined volcanic activity, the drift of land masses, and the patterns of ocean currents beneath the surface. Most believed that the drivers of the planet's past lay entirely within its own boundaries. They viewed Earth as an isolated entity, adrift in emptiness, like a solitary vessel. Milankovitch dismantled that notion. He saw that comprehending the planet's bouts of warmth and cold required more than inspecting the subject itself. You must consider its surroundings. He recognized Earth as an open system, fueled by one primary outside source, the sun. All the radiant power that stirs the breezes, propels waterways, and nurtures woodlands originates from that distant star. Thus, the planet's climate hinges on a straightforward formula: the quantity of solar energy arriving and its distribution across the globe. For ages, experts presumed this dynamic remained unchanging. The sun flares consistently. Earth orbits it reliably. Seasons arrive and depart predictably. Yet Milankovitch spotted the flaw in such a rigid view. He understood the solar system isn't a desolate arena but a bustling domain. We occupy it alongside behemoths like Jupiter and Saturn, immense gas worlds whose gravity vastly overshadows ours. We also coexist with nearer stone siblings such as Venus and Mars. Gravity acts as an unseen bond, feeble yet boundless, extending through the void. Consequently, as Earth circles the sun, it doesn't follow a flawless, solitary route. It's being deflected, it's being drawn, It's being gently steered by Jupiter's gravitational influence, yanked by Saturn's periodic approaches. These effects are faint. Over one orbit, they register as negligible, but duration amplifies them profoundly. Across millennia, these delicate, periodic gravitational nudges build up. They start to distort our world's course. They initiate a slant. They induce a sway. Milankovitch perceived that Earth's stance in the cosmos isn't stationary. It's in motion, like a dance. This motion alters how sunlight strikes the ground. It might not alter the overall solar input to the planet, but it shifts the spots where that warmth concentrates, and vitally, its timing. He pinpointed three specific motions, three separate components in the astronomical mechanism, each operating at its distinct pace. Each impacts the weather uniquely. When these elements synchronize, they can redirect northern sunlight, allowing winter snow to linger through summer and ushering in global glaciation. We often imagine the solar system as a flawless, harmonious device, a paragon of mechanical precision, where worlds glide on unseen rails, detached and unaware of each other. But gravity ignores such divisions. It's unending, fading with separation, but never vanishing completely. Amid the dark quiet of the cosmos, Earth isn't solitary. It's encircled by titans. Well past Mars's path dwells Jupiter, a world so enormous it holds over twice the mass of every other planet together. It's an aborted star, a gigantic gaseous sphere whose pull stretches across vast distances. Farther out is Saturn, yet another colossus, encircling the system with its formidable gravity. As Earth hurtles around the Sun at 67,000 miles per hour, it repeatedly crosses the gravitational trails left by these giants. Each encounter with Jupiter delivers a pull, a faint, barely noticeable jolt, a soft gravitational murmur. A single instance would be insignificant, but these occur repeatedly, endlessly, over eons. It's akin to swinging a child. A lone soft shove achieves little. Yet timing each push precisely as the swing returns lets the momentum build. The swing arcs farther. The oscillation intensifies. This underlies orbital resonance. Due to the persistent cyclical pulls from Jupiter and Saturn, Earth's solar journey isn't rigid. It's adaptable. It fluctuates. The orbital path elongates, turning into a drawn-out music ellipse that drags our planet millions of miles away from the sun's comforting glow. Gradually, influenced by shifting gravitational alignments, it contracts once more into music, almost a flawless circle. Our world rotates like a spinning top, yet the gravitational forces from the moon and sun cause it to tilt. Its music axis sways up and down. This represents the intricate machinery of the cosmos. An intricate, unpredictable music, yet mesmerizing interplay of forces. Earth gets tossed between the sun and those massive gas giants, a tiny rocky body swept up in the currents of gravity. Milankovitch discerned that this intricate motion divides into three clear components, three precise music mechanisms that shape our planet's climate. The biggest, slowest, and most influential is the orbit's form itself. This primary mechanism in the cosmic timepiece moves at a glacial pace, yet it establishes the rhythm for every ice age. Known as music eccentricity, it operates over immense timescales of about 100,000 years, driven by the relentless pull of Jupiter and Saturn on Earth. They distort our trajectory, reshaping it from a tight circle into a stretched oval loop, only for it to gradually revert. This is the music expansion. Its importance lies in how it governs separation. A round orbit keeps Earth at a steady, even distance from the Sun throughout the year, delivering consistent warmth. But during high eccentricity, when the path stretches out, music, our planet, ventures deep into the frigid void of space before arcing closer again. At the ellipse's farthest reach, music, we're positioned millions of miles beyond our typical solar proximity. Like stepping back from a campfire. Solar radiation hitting the surface diminishes overall. Winters stretch a bit longer. Summers grow a touch milder. The world gets less energy input. Crucially, this full cycle of expansion and contraction spans music, precisely 100,000 years, aligning exactly with the patterns etched in ice cores. The jagged music profile from Vostok, the advance and retreat of vast ice sheets pulse in lockstep with our orbital music elongation. Farther from the sun, ice expands. As the circle tightens, it melts away. This forms the core beat, the 100,000-year throb of glacial epochs, essentially charting our varying closeness, music, to the star that sustains us. Yet, mere distance won't encase a world in frost. Chill requires direction. Enter the music's second mechanism. Eccentricity determines our remoteness from the heat source, but the next one controls music, a more nuanced and perilous aspect, the way sunlight bathes our surface. This is obliquity, music, the axial lean. Imagine Earth, not as a fixed model, but as a whirling top. A rapidly spinning top holds steady, music, and vertical, but if it decelerates or faces unseen pressures, it starts to lean, tracing a gentle, swaying rhythm against the ground. That's our Earth, music in the void, twirling at 1,000 miles per hour and leaning all the while. We're told the planet's tilt stands at 23.5 degrees to the sun, the ideal slant that creates seasons. Music. Northern summer comes when the hemisphere faces the sun. Music winter when it turns aside. It powers our annual cycles. But 23.5 degrees isn't eternal. It's just our current state. Across 41,000 years, music, the tilt, gently oscillates between a modest 22.1 degrees and a sharper music, 24.5 degrees. A mere 2 degrees swing, hardly noticeable on a measuring tool. Yet for a world, it's the line between lush growth and frozen waste. This leads to the Ice Age puzzle. Most folks blame harsh winters for glaciations, logical enough. Fierce cold should lock everything in ice. But Milankovitch saw the flaw. He grasped a deep weather principle. Brutal winters don't forge ice caps. Music, in truth, the coldest ones tend to be arid, depriving glaciers of water. The real force behind an ice age isn't winter, it's summer. Think about how a glacier forms. Snow accumulates to create it. Each winter, fresh snow blankets the northern reaches of Canada, Scandinavia, and Siberia. That's just routine. The real turning point hits in July. Summer's role is to thaw that accumulation entirely, clearing the way for the following winter. If temperatures soar, the snow disappears completely, leaving the landscape verdant. But suppose Earth's axial tilt dips to 22.1 degrees. The summer sunlight then hangs lower in the sky. Its beams arrive at a grazing angle, weakened and scattered by the air layers above. It provides illumination, yet delivers scant warmth. Here, summer falls short. The rays gleam but lack the intensity to dissolve the prior season's buildup. The snow endures. It persists from June into July and August. This persistent layer clings to the earth, pale and unyielding, bouncing the feeble rays back toward the cosmos. Come September, another winter sets in. New flakes, settle atop the enduring base. That's the genesis of an ice epoch, a remnant from one winter that a feeble summer couldn't remove. Season by season, this surplus piles up. The pressure from fresh deposits compacts the older ones. Flakes compress, shedding their trapped air. They evolve from fluffy crystals into dense neve. Eventually, under crushing force, they solidify into translucent blue ice. This process repeats across millennia. The mass expands, creeping under its own mass. It engulfs valleys and spills over peaks. Such is the influence of the tilt, the 41,000-year rhythm that governs seasonal intensity. A steeper tilt amplifies contrasts. Scorching summers dissolve any frost. A shallower one tempers them. Temperate summers let ice endure. This mechanism, this axial sway, decides if snow thaws or erects a frozen legacy. Yet one more component remains. It's quicker, more erratic, and utterly bewildering than the rest. An oscillation that alters not only seasons, but the night sky too. The initial cycle elongates the path. The next tilts the pole. This third one disrupts most profoundly. It redefines our cosmic orientation. Enter precession, the axial wobble. Observe a top in motion. It doesn't remain upright. Its axis scribes a gradual looping path as it rotates. Earth mirrors this precisely. Currently, the North Pole aligns with Polaris, our steadfast North Star. It's the reliable guide that seafarers have relied on for ages. We take its constancy for granted. It's illusory. The sun and moon's gravity, pulling on our planet's equatorial bulge, gradually torques the axis. The North Pole inscribes a vast arc across the heavens. 12,000 years back, ancient peoples gazed at Vega, a dazzling blue-white beacon, not Polaris. In another 12 millennia, Vega will reclaim that role for our heirs. Polaris will fade into obscurity among the stars. This pattern spans about 23,000 years. It's the swiftest tick of the celestial timepiece. But how does axial orientation affect weather patterns? Why does the targeted star influence climate? It counts because our orbit isn't perfectly round. Recall the eccentricity, the elongated path. Earth reaches perihelion, nearest the sun, and aphelion farthest. Precession shifts which season aligns with those extremes. That's pivotal. Today, fortune favors us. The North experiences winter at perihelion. Our colds are thus less severe, drawing nearer the solar blaze in darkest times. Still, the wobble advances. In about 10,000 years, the alignment will reverse. Northern winter will coincide with aphelion, plunging us to maximal distance in icy void, while summer hits perihelion amid stellar fury. This yields wild swings. When precession syncs with eccentricity, it forges hyperseasons, savage winters and blistering heats, or conversely, gentle colds and subdued warms. And recall, subdued summers hold the secret. Precisely tuned, the wobble orients the north, home to vast expanses like Canada and Siberia, to capture the least summer insulation possible. It saps the season's melting might. Thus, the third element acts as the precision adjuster. This mechanism acts as a frequency adjuster, intensifying or neutralizing the impacts of the other two components. At that point, Milankovitch possessed every element needed. He identified the 100,000-year orbital extension, the 41,000-year axial tilt, and the 23,000-year precession cycle. Individually, these influences offer only subtle shifts. Yet Milankovitch understood that these rhythms intersect. They intertwine like threads in a fabric. Periodically, Much like the mechanisms of a vast astronomical vault falling into alignment, they synchronize completely. In those instances, they unlock the pathway to glaciation. On their own, such factors lack strength. An elongated path around the sun alters incoming light by barely a percentage point. A reduced inclination lowers summer temperatures by just 1 degree. A precessional shift adjusts seasonal timing by mere weeks. Alone, they amount to little more than faint solar static. However, Milankovitch recognized time's role as an intricate artisan. It gathers these distinct strands, the 100,000-year extension, the 41,000-year inclination, and the 23,000-year axial sway, and intertwines them into a single chord. Typically, these patterns counteract one another. The orbit may draw Earth farther from the sun, yet a strong tilt delivers intense summers capable of dissolving ice. They balance out, maintaining equilibrium. The climate holds steady, and the world stays verdant. But roughly every 100,000 years, the elements converge. The components of that immense astronomical mechanism engage precisely. This creates a phase of amplified synergy, an ideal convergence of chill. Picture the conditions unfolding. Initially, eccentricity peaks, elongating Earth's path into an extended ellipse. We find ourselves millions of miles distant from the sun's intense core. Next, precession repositions the axis, ensuring the northern hemisphere's summer coincides precisely with Earth's remotest, coolest position in that ellipse. The midsummer sunlight arrives faint and remote. Finally, obliquity diminishes. The planet assumes a more vertical posture, with the axial lean hitting its lowest point so that feeble, far-off summer rays hit northern regions at a low grazing incidence. It's a coordinated assault. Separation, season, and incidence all collude to deprive the north of warmth. Insolation over places like the Canadian Arctic or Scandinavian uplands plummets sharply, dipping under the vital limit. Winter snowfall persists through the summer thaw. It endures, accumulating across successive seasons. Confined in his prison quarters, Milankovitch computed these patterns manually. He sketched charts, forecasting the precise timing of past alignments. He anticipated glacial epochs long before ice core samples existed. He discerned the inescapable logic of those freezes in the equations. Still, a flaw persisted, a theoretical shortfall that troubled him deeply. The calculations reveal that even this ultimate orbital convergence only diminishes overall insolation modestly. It's a notable decline, certainly, but insufficient on its own to encase a world in frost. Not enough to erect kilometer-thick ice masses. The figures suggest mere temperate cooling. The rocks tell of a world locked in ice. An essential element was absent. These orbital rhythms served as the spark, yet not the explosive force. Some terrestrial process had to seize that faint chill cue and escalate it dramatically. An earthly dynamic needed to transform the murmur into a roar. The equations were impeccable. The patterns matched. Milankovitch had charted the pulsing rhythm of the solar dance flawlessly. Yet a spectral inconsistency lingered, a puzzle that shadowed the model for years. When experts tallied the precise thermal deficit from these celestial shifts, the results proved disappointingly minor. In the most extreme alignment of inclination, precession, and eccentricity, the net decrease in solar input to Earth remains surprisingly modest, akin to a subtle dimming of a light source. It ought to yield gentle moderation. A couple of degrees cooler in the Arctic, Winters extended by a bit. Not the smothering of North America beneath 3 kilometers of glacier. It posed a riddle. The celestial rhythms were a murmur, but the climatic archives revealed thunder. The globe responded with ferocity far beyond what the incoming radiation warranted. It resembled a light brake touch causing a vehicle to veer wildly. This insight drove scientists to a key understanding. Earth isn't an inert chunk. It's no lifeless orb passively absorbing solar warmth. Our planet functions as an interactive network, equipped with its own mechanisms, controls, and latent energies. The orbital variations merely initiate the process. They're the switch that starts the motor. But the true propulsion for the glacial era resides inside the world. We term these amplifying processes feedback mechanisms. These processes transform a minor shift into a massive escalation, multiplying its impact until it spirals out of control. Milankovitch had identified the underlying pattern. Yet, to grasp the onset of glaciation, we must explore how Earth seized that faint orbital cue and turned it into a self-destructive force. Our world possesses 2 primary intensifiers, 2 systems that convert mild chill into profound refrigeration. One relies on illumination, the other on atmosphere. The initial one functions akin to a reflector. This primary intensifier operates on a basic color dynamic. Picture traversing a sweltering blacktop lot during peak summer heat. The surface scorches, sending warmth upward through your footwear. Now shift to a strip of pale pavement. Notice the relief from the heat. That's the albedo effect at work, quantifying how much light bounces back. Shadowy expanses like midnight seas, lush boreal woods, or earthy terrain greedily soak up solar rays. They capture the glow, transforming it to thermal energy that heats the overlaying air. A globe dominated by woodlands and waters craves warmth. In contrast, pale expanses behave differently. Glaciers and frost serve as Earth's reflectors, spurning warmth absorption. Instead, they repel sunbeams, hurling them skyward through the air layers and into the icy void beyond. An ice-clad world clings to its frigidity. Such dynamics spawn a perilous cycle. As Milankovitch rhythms align, elongating paths and reducing axial lean, northern summers lose their potency. Scattered snowfields in regions like the Canadian uplands or Scandinavian peaks endure past the height of midsummer. Initially, these spots seem trivial, mere pale specks amid darker terrain. Yet their pallor grants them potency. They deflect the feeble rays, chilling the air overhead. This localized drop aids the snow's persistence and prompts additional flakes nearby. The pale area swells. Expanding, it mimics an enlarging reflector, repelling greater volumes of light. The zone cools further. Greater chill invites heavier snowfall. More accumulation enlarges the reflector anew. Thus, unfolds the ice albedo loop, a prophetic escalation, surpassing a threshold, say, blanketing Hudson Bay or the Baltic expanse. The momentum halts resistance. Earth ceases to resist the frost and instead engineers its spread. The sprawling northern ice caps transcended mere solidified liquid. They formed vast continental barriers. During the last glacial maximum, the expansive pallor over North America and Eurasia hurled immense solar influx away from the globe. Effectively, the planet averted its gaze from the stellar blaze, forsaking the vitality that might have thawed it. This process illuminates how diminished insulation ignites regional icing and fuels glacial advance. However, glacial epochs transcended regional bounds. They enveloped the globe. Northern solidification chilled the south as well. Equatorial zones desiccated. From equator to poles, the world synchronized in descent. A solitary reflector in Canada can't temper Amazonian heat. For frost to dominate universally, Earth required another escalator. It needed a conduit relaying the glacial Q worldwide. It demanded alteration of the very air. Icy reflectors account for northern lock-in but not planetary pursuit. As ice fronts overran Canada, Amazon basins chilled correspondingly. African arid lands shifted, pole to pole. Uniformity prevailed in the frost. Local reflection falls short here. Global thermal overhaul necessitates atmospheric overhaul, diluting the insulating shroud. Enter the second major escalator, the pilferer. That pilferer, the seas. Grasping this hinges on a simple analogy, a fizzy drink in a bottle. Exposed to scorching rays, it loses effervescence swiftly as bubbles flee. Chilled thoroughly, however, the fizz remains locked within. Cooler liquid retains more dissolved gases than heated versions. This stems from core physico-chemical principles. With Milankovitch influences, sparking initial northern moderation, and icy reflectors, increasingly repelling rays, worldwide sea temperatures fell. Cooling waters grew voracious, drawing in gases. Seas commenced extracting carbon dioxide from the air. Vast quantities, billions of metric tons of insulating vapor, vanished into oceanic depths. Atmospheric CO2 diminished, weakening the greenhouse veil. Heat retention waned planet-wide. This intensified the global drop, further cooling seas and boosting their gas uptake. A relentless plunge ensued into glacial profundity. Yet the sea employed a more dynamic method to sequester the heavens. It harnessed biology. With the expansion of terrestrial ice masses, they pulverized the underlying rock into nutrient-laden powder. Blasted across the seas by powerful winds from the glaciers, this powder served as a colossal nutrient boost. Oceanic surface layers burst forth with vitality. Plankton, those minuscule photosynthetic organisms, flourished in enormous, spiraling blooms visible even from orbit. These infinitesimal beings absorbed the leftover atmospheric CO2 to construct their structures. Upon death, they avoided decomposition at the surface. Instead, they plummeted downward. A perpetual cascade of lifeless organic matter rained into the oppressive depths below. It accumulated on the ocean bottom, trapping that carbon for millennia. In essence, the sea had stripped the air of its warming shield. That's precisely why the Vostok ice cores reveal CO2 and temperature tracking each other precisely. A drop in CO2 meant a plunge in warmth. Orbital variations sparked the process. Ice caps amplified it like reflectors. But the ocean's quiet plunder of the atmosphere transformed a local chill into a worldwide glaciation. The mechanism was complete. The initiator, reflector, and pilferer collaborated seamlessly. Earth braced for the extended pale season. The snare activated. Orbital mechanics pulled the lever. The ice reflected solar rays while the waters entombed the warmth. At this point, the continental makeover truly commenced. We commonly picture ice ages as relentless snowstorms, turbulent and blinding white chaos. Yet the advance of these vast ice formations was probably much subtler and far more ominous. It unfolded as a gradual, relentless smothering. The process started in elevated regions. On Canada's Keewatin Plateau and Scandinavia's peaks, snowfall persisted without thaw. Season by season, accumulations mounted, 10 feet, 50 feet, 100 feet. Once reaching a pivotal depth, snow's properties shifted. Basal crystals compacted beneath the overlaying burden, merging and expelling air, evolving from airy flakes into compact azure glacial stone. The mass started to shift. It moved like a sluggish stream of syrup. Pulled by gravity, icy protrusions inched from uplands, flooding vales, engulfing woodlands, and inundating basins. Unlike today's alpine glaciers hugging slopes, these were expansive sheets, dome-like expanses reshaping the land. The mightiest was the Laurentide ice sheet. It engulfed almost all of Canada and much of the northern U.S. It devoured the Great Lakes. It submerged sites now known as Chicago, New York, and Boston. At its core, above Hudson Bay, it rose as a colossal mound exceeding 3 kilometers in height. Picture yourself at the foot of an icy barrier, soaring into the upper atmosphere, taller than the Rockies. Its sheer scale disrupted planetary spin. It diverted the jet stream, rerouting air currents and reshaping northern weather across the hemisphere. In Europe, the Fennoscandian sheet advanced southward, overtaking the British Isles and Scandinavia, extending to Berlin and Moscow. These pale behemoths were immense, frigid, and impassive. They abraded the terrain to bare stone, functioning as enormous abrasive plains, obliterating streams and sculpting the contours we traverse now. As they expanded, they imposed another effect. Their mass intensified, so profoundly heavy that they deformed Earth's outer shell. Water carries weight. Anyone lugging a brimming pail understands. 1 cubic meter equals a metric ton. Envision that frozen across vast distances, piled 3 kilometers deep. The load was staggering. Such pressure overwhelmed the crust that apparently unyielding bedrock. It yielded, flexing downward. We view land as a sturdy base, but geologically, the crust resembles a buoyant platform atop a dense, fluid layer of heated stone, the mantle. Add substantial cargo to a float, and it dips. Beneath the Laurentide and Fennoscandian burdens, North America and Europe subsided outright. Firm lithosphere plunged nearly a kilometer into the mantle. The ice forged its own depressions. It molded rounded terrains into scooped hollows. Canada's Hudson Bay echoes this force, a subsidence from the dome's epicenter, where compression peaked. This descent wasn't swift. It was a drawn-out, grinding capitulation of stone, and rebound has crawled at a similar pace. This stands as the most eerie remnant from the Ice Ages. Even though the ice vanished 10,000 years ago, the ground hasn't forgotten its burden. It's still bouncing back gradually. Scientists refer to this process as isostatic rebound. At this very moment, while you're hearing these words, the terrain across Scandinavia and northern Canada continues to elevate. It's emerging from the ocean at about a centimeter annually. The old Viking shorelines now lie deep inland, hoisted well above the surf by the crust's deliberate, creaking rebound. Earth remains in recovery from that deep scar. Yet, as those landmasses sagged beneath the glacier's mass, profound shifts unfolded elsewhere on the planet. The moisture needed to form those towering ice behemoths came from a specific source. No magic conjured the ice sheets. They drew from the oceans themselves. With the ice expanding, sea levels dropped significantly. The globe's geography underwent a complete overhaul. Erecting an ice peak reaching 3 kilometers in height required draining vast amounts from the seas. The immense quantity of water trapped in the Laurentide and Fennoscandian sheets was mind-boggling. It sufficed to reduce worldwide ocean levels by 120 meters, equivalent to a 40-story building. Picture yourself on a shoreline amid the last glacial maximum. Instead of waves caressing your toes, the sea would be absent. It appeared as a faint azure streak far off on the horizon, separated by miles of blustery, salt-encrusted flatland. The standard world map, with its continental outlines from classroom models, dissolved away. The British Isles weren't isolated anymore. They formed elevated ridges on an expansive, flattened European landmass. A pedestrian could stroll from London to Paris or Amsterdam to Newcastle without a single splash. You'd traverse Doggerland, a fertile tundra plain alive with mammoth and reindeer packs. Territory now submerged under the North Sea's chilly swells. Farther east, the divide between Asia and North America vanished, with no water barrier in place. The Bering Strait, that slim waterway linking Russia and Alaska, transformed into a broad, firm expanse known as Beringia. It functioned as a transcontinental thoroughfare, a sprawling prairie pathway spanning thousands of kilometers that enabled species to migrate between the continents. The Earth seemed physically bigger then. Coastal shelves lay bare under the sky. Conditions grew more arid and dusty overall. Trapped in ice, so much water meant worldwide precipitation crashed. Equatorial jungles contracted to scattered refugees, giving way to expansive savannas. The era wasn't solely frigid. It was parched as well. Within this depleted, broadened landscape, organisms adapted and thrived. They didn't merely survive the chill. They exploited the altered terrain to relocate. Glaciers sealed off northern passages, but receding waters unveiled routes for the most epic migration ever. Those ice masses loomed like impenetrable barriers, snowy citadels obstructing the northern vista. However, by siphoning the seas, they unwittingly constructed connections. For Pleistocene life, the Ice Age brought not stagnation but extraordinary movement. Sure, temperatures plunged, but global linkages formed unlike anything now. Continental isolation shattered. The massive Eurasian and American landforms, typically divided by the Pacific's turbulent, icy currents, merged via the Bering Land Bridge. Labeling it a mere bridge undersells its scale. This was a subcontinent comparable in breadth to contemporary France, a vanished realm that persisted for millennia before sinking once more. Far from a frozen wasteland, it defied common myths of the Ice Age. We often envision a realm smothered in endless drifts. Yet, with water bound in glaciers, the atmosphere turned exceptionally arid. Precipitation fell short in numerous regions to sustain more ice buildup. Rather, an extraordinary, long-gone biome spanned the northern realms. Known as the Mammoth Steppe, it evoked an endless grassland running seamlessly from Spain's shores through all of Russia, over the land bridge, and into Canada's Yukon. A boundless, gusty expanse of parched, nutrient-rich grasses and shrubs, harshly cold, barren and gritty. The winds howled relentlessly, but during summer, bathed in non-stop daylight at those elevated latitudes, the steppe burst into vibrant growth. It sustained animal populations matching today's African Serengeti. Woolly mammoths, ideally suited to this icy, desiccated environment, foraged beside woolly rhinoceroses. Vast bison herds stampeded over the steppes, pursued by cave lions and scimitar-toothed cats. It was a realm dominated by colossal beasts, an icy counterpart to the Serengeti. Trailing these groups, slipping stealthily amid the grasses, prowled the ultimate hunter, humanity. The Ice Age didn't halt our wanderings. It propelled them forward. Lower sea levels exposed new coastal pathways. During short, warmer intervals, green pathways emerged between the ice sheets, serving as conduits that guided groups northward. For early humans, the glacial period represented an opportunity. As the world grew drier, it pushed them from dwindling woodlands onto vast open grasslands. The chill compelled them to adapt, mastering fire, crafting intricate garments, and constructing protective dwellings. They trailed the mammoths' migrations. From Siberia, they trekked into Alaska, unaware they were bridging continents, driven only by the lure of vegetation and game. They settled on the land bridge, not merely passing through but establishing homes. DNA studies indicate that people might have lingered in Beringia for millennia. This Berinian pause, hemmed in by icy barriers to east and west, allowed for the development of unique genetic traits that later spread across the Americas. The frigid conditions acted like a crucible, hardening both wildlife and humans by eliminating the frail and rewarding the resilient. For millions of years, this pattern persisted. Ice expanded, seas receded, pathways formed, and species migrated. Eventually, the ice thawed, waters surged, connections vanished, and life diversified in seclusion. It formed an ideal recurring cadence, a 41,000-year pulse, dictating movements, adaptations, and disappearances. Yet something unexpected occurred. The tempo faltered. The astronomical mechanism missed a step. Roughly 1 million years ago, the long dominant earthly pattern abruptly altered. Winters lengthened, ice deepened, and the rhythm decelerated. For almost 2 million years, the planet operated like a reliable mechanism. Deep ocean sediment layers reveal a distinct, steady, unyielding sequence, throbbing to a 41,000-year tempo. This reflected the axial tilt's influence, as Earth tilted side to side on its axis. Ice masses advanced and withdrew in harmonious response. It created an even-keeled realm. Glacial eras came often but stayed gentle. Interglacials arrived regularly, yet remained tempered. Equilibrium defined the era. However, around 1 million years ago, a flaw emerged in the system. Scientists term this the mid-Pleistocene transition. It stands as one of the greatest enigmas in planetary climate history. Suddenly, and with no apparent external trigger, Earth's vital rhythm decelerated. It faltered once, then again. The 41,000-year pattern dimmed. Instead, a prolonged, far harsher cadence took hold. The interval extended to 100,000 years. This shift went beyond mere duration. It amplified ferocity. In the prior system, ice sheets resembled gentle waves lapping at northern terrains before swiftly pulling back. But in the new 100,000-year era, the ice turned relentless. It grew defiant. Glaciers ignored the tilt's cues to retreat, enduring through warmer orbital phases. They bulked up, chilled further, and gained mass, accumulating for 90,000 years, achieving scales and extents unprecedented on the planet. When they at last receded, the melt was abrupt and catastrophic, producing the jagged, saw-like profile evident in Antarctic ice samples. This is the core puzzle, the element that perplexes researchers endlessly. The sun remained unchanged. The Milankovitch cycles, the orbital stretch, the axial lean, the precession, proceeded unaltered. The celestial gears didn't lag. The extraterrestrial input stayed consistent. Yet Earth ceased responding. It disregarded the bold, straightforward tilt signal and instead attuned to the weaker, more nuanced eccentricity beat. Imagine a receiver dismissing a vibrant dominant station and locking onto a distant hazy murmur, boosting it to overshadow all else. Why? What prompted the world to embrace harsher, extended winters? Why did the ice grow so unyielding? The explanation, experts think, resides not above but under the frost itself. It stems from the interface of glacier and bedrock. The Earth altered its surface. The key to the 100,000-year enigma hides in the soil. To grasp the ice's newfound dominance, examine its foundation. Prior to the onset of ice ages, North America and Europe differed greatly from today. They lay beneath a substantial blanket of unconsolidated earth, broken down stone, and time-worn deposits. Experts dubbed this regolith. It represented the buildup from eons of erosion. When initial glaciers arose about 2 million years back, they rested atop this regolith. Picture loose earth as a bed of rollers. It offers minimal traction. As the ice sheets expanded over this layer of soil, they proved highly mobile, gliding with ease. They extended outward in broad, rapid sheets. Yet their thinness and perpetual motion left them exposed and fragile. During the 41,000-year tilt cycle, which ushered in marginally hotter summers, these slim, slick ice formations disintegrated rapidly. They thawed completely. Glaciers, however, extend beyond mere frozen liquid. They rank as nature's mightiest earth movers. With each advance and withdrawal in those initial cycles, the ice functioned like an enormous abrasive layer. It eroded, carved deep grooves, and shoved the regolith toward the seas. Over 1 million years, this relentless glacial action gradually bared the continents. Then, roughly 1 million years ago, the process concluded. The soft, unstable ground had vanished. The Canadian Shield and Scandinavian mountains stood exposed to their unyielding crystalline bedrock. The dynamics of the ice shifted abruptly. No longer perched on slick dirt, the glaciers now rested on jagged, high-friction rock. The ice adhered firmly. It clutched at the stone. This heightened drag prevented the sheets from sliding freely anymore. Rather than flattening out thinly, they started stacking upward. They accumulated in greater heights, turning denser, more vertical, and chillier. They transformed into impregnable ice bastions. Their immense thickness and low temperatures granted them fresh resilience. When the 41,000-year tilt cycle returned to heat the globe, these adhesive ice masses shrugged it off. The summer's mild temperatures couldn't breach the stronghold. The ice endured the feeble warmth and continued expanding. It disrupted the previous pattern. It lingered. It bulked up through another 40,000 years, and yet another, until it swelled to a precarious, enormous scale where only the dominant 100,000-year eccentricity cycle could topple it. The world altered its tempo by shedding its outer layer. In eroding the soil, Earth unwittingly created its own snare, enabling the ice to evolve into the colossal forces that shaped the past 1,000,000 years. Yet even behemoths reach their limits. And when the 100,000-year cycle strikes at last, the Ice Age's close isn't a gentle ebb. It's a cataclysm. For 90,000 years, the ice accumulates steadily, a patient, unyielding drain on ocean volumes and atmospheric warmth. But an Ice Age's conclusion lacks patience or gradualness. It's a rupture. In paleoclimatology terms, this isn't mere thawing. It's termed a termination. The term evokes brutality, and fittingly so, when the 100,000-year cycle converges to unleash heat. As the orbit elongates, the axial tilt intensifies and the precession directs the North Pole sunward. The ice bastion faces assault on every front. Solar rays hammer with intensified force. Carbon dioxide, liberated from the heating southern seas, saturates the air. The towering, precarious ice sheets start to decay. They don't just drip away slowly, they fracture. Enormous meltwater pools, rivaling inland oceans, form atop the glaciers. Mounting pressure fissures the ice, funneling countless gallons through steep chutes known as moulins to the underlying bedrock. This deluge serves as a slick agent. The grip that anchored the ice evaporates. Entire ice sheet sections unravel. They plunge seaward in flotillas of icebergs, a phenomenon dubbed a Heinrich event. These colossal armadas clog the North Atlantic, disrupting flows and reshaping planetary weather. Inland, the thaw wreaks havoc. Ice barriers containing lakes of trillions of tons give way. The ensuing colossal floods defy contemporary understanding. Towering water walls, hundreds of feet tall, scour the terrain, eroding soil to bare rock within days. The scablands of Washington state bear the marks of one such ferocious outburst, and the seas, they swell. Not inching up gradually, but surging in bursts called meltwater pulses. Worldwide, sea levels can climb meters within one person's span. Continental margins submerge. Land connections, like Beringia and Doggerland, vanish beneath the tides. The world's geography redraws itself in frenzy. New islands emerge, peninsulas detach. This marks the grand dissolution. It traces the sharpest ascent on the jagged paleoclimate chart. A 90,000-year freeze unravels in mere millennia of turbulent, sodden, and savage renewal. Once the waters calm, once the ice withdraws to polar realms and shores steady, an altered landscape emerges. A balmy, moist, remarkably steady realm. One permitting a nomadic primate lineage to halt its flight, sow crops and erect barriers. The savage surges of those meltwater deluges eventually subsided. Sea levels held firm. The shorelines, which had shifted inland over countless millennia, at last reached their equilibrium. Then, roughly 11,700 years ago, our planet accomplished something it hadn't managed in ages. It calmed down. Over the prior 2 million years, the climate had resembled a wild ride. It traced a turbulent path of icy plunges and scorching surges. Weather patterns delivered relentless, erratic shifts. Someone born in one era could thrive in verdant meadows, only for their descendants to face barren wastelands. Yet the emerging era, the Holocene, broke that mold. Glance at the climate chart spanning the past 10,000 years. It's no erratic zigzag. Instead, it forms a remarkably even stretch. This era represents a sustained phase of mild temperatures, like an extended serene dusk in Earth's timeline. Such steadiness marks the Holocene's anomaly, and it stands as the pivotal geological reality shaping human history. Think about the chronology. Modern humans, in anatomical terms, have roamed this planet for no less than 300,000 years. Throughout, we've possessed identical intellects, dexterous limbs, and the same potential for speech and innovation. Still, across 95% of that span, we erected no lasting structures. We skipped agriculture. We avoided urban settlements. Existence meant nomadic life, tight-knit groups of foragers trailing animal migrations, perpetually adapting to an ever-shifting environment. Our intelligence was sharp, but we bowed to the turmoil of Milankovitch forces. Farming, proves impossible when precipitation cycles alter across lifetimes. Urban development falters if oceans advance a meter per decade. Then came the Holocene. Temperatures confined themselves to a dependable band. Precipitation turned consistent. Seasonal rhythms grew dependable. Suddenly, across the world, people halted their migrations independently. In the Fertile Crescent, we sowed grains. In China, we domesticated rice. In the Americas, we raised sacred structures. We pioneered scripts, arithmetic, and societies. All that defines us, from initial clay bricks to the International Space Station, rests upon this tenuous bedrock of climatic constancy. We owe our origins to the Holocene. Yet when scientists scrutinize this idyllic period more intently, unease creeps in. Comparing it to earlier balmy intervals, the pauses amid glacial epochs reveals oddities. Typically, those warmer spells prove brief. They spike abruptly, linger for mere millennia, then swiftly descend toward chill. Under Milankovitch principles, the Holocene ought to have concluded eons back. Its zenith has waned. The configurations of orbits driving the massive thaw have diminished. Sunlight at the 65th parallel now diminishes. Per the celestial timetable, the festivities should have wrapped up. Glaciers ought to be advancing. Ice sheets should be inching southward from Baffin Island and Norway at this very moment, but they're not. This extended thaw persists. The rhythm appears jammed. That discrepancy sparks our deepest apprehension. Is this steadiness innate, or have we unwittingly disrupted the mechanism? Adhering to cosmic directives, honoring the pull of gravity that has ruled Earth for 1,000,000 years, would mean our prosperous phase has expired. We're existing on extended credit. Astrophysicists examining Earth's present alignment find the data starkly clear. The Milankovitch apparatus grinds toward refrigeration. Planetary inclination lessens, gradually aligning straighter and muting summer's vigor. The axial precession positions northern summers farther from solar proximity. The elliptical path evolves. Every calculated indicator signals the warm interval's closure. Insolation across the Arctic's vital zones, the 65th parallel north, declines. Remarkably, today's Arctic sunlight mirrors levels from 115,000 years past. And 115,000 years ago marked the onset of the preceding glacial advance. So, why no frost? In reality, Earth did attempt a return to frigidity, striving to adhere to its rhythm. Around 5,000 years ago, the Holocene's apex warmth subsided. The planet slipped into what's termed the neoglacial by geologists, a halting, uneven drift coolerward. In Siberia, forest boundaries pulled back southward. In the Swiss Alps and Norway, long dormant glaciers stirred, advancing into vales and entombing woodlands from balmier days. This chill's peak arrived quite lately. We know it as the Little Ice Age. Between the 14th and 19th centuries, the globe quaked with cold. London saw the Thames River freeze over so solidly that festivals unfolded atop the surface. It marked an era when Viking settlements in Greenland, which had thrived on lush meadows for generations, succumbed to starvation and faded away as encroaching sea ice sealed off their shores. It brought widespread hunger and crop failures throughout Europe. This wasn't mere chance. It signaled the onset. It represented the initial hesitant descent along the extended path toward the upcoming glacial peak. Our world was reacting to the Milankovitch influence. The reflective surfaces were attempting to emerge. The oceans were drawing in breath. The entire mechanism was functioning just as it had throughout history. Yet suddenly, the chill halted. In what amounts to an instant on a geological time scale, the pattern flipped. The plunge toward frigid conditions didn't merely pause, it crumbled apart. Temperatures didn't stabilize, they surged skyward. Glaciers that had expanded amid the Little Ice Age didn't simply pull back, they started dissolving. Arctic sea ice, expected to grow denser at this point, instead grew more fragile. The celestial timer continues its rhythm. Jupiter's gravitational pull persists. The axial lean keeps diminishing. The call for a prolonged winter echoes strongly across the solar system, yet Earth has tuned it out. Something has disrupted the machinery. A fresh power has disrupted the formula. A power strong enough to counteract the pull from massive gas planets and the sun's orbital layout. And this power didn't originate from space. It arose from beneath our feet. It stemmed from the blazes ignited by one particular species that figured out how to liberate carbon stored from the Carboniferous era. The element that halted the frost didn't descend from above. It welled up from the earth. Over eons, the carbon remnants of bygone eras lay securely entombed. The vast woodlands of the Carboniferous, the microscopic life in Jurassic seas, all transformed into coal and petroleum, hidden deep in shadows. They served as the world's dormant spirits. Then in the flicker of a geological moment, a single species chose to rouse them. We label it the Industrial Revolution. But from Earth's perspective, it was a surge of carbon. Humanity extracted the petrified rays of sunlight from 300 million years past and unleashed them into the air over just 200 years. We hijacked the carbon cycle, a cycle that normally unfolds across thousands of years, and propelled it forward at a detonative pace. The impact on the Milankovitch process was staggering. Recall the fragile equilibrium needed to trigger an ice age. The elliptical path extends, allowing Earth to lose warmth. The reduced obliquity diminishes summer intensity, but these effects are nuanced. They depend on an atmosphere sparse enough for heat to dissipate. Researchers have determined a precise limit, a critical value for launching a glacial era. To initiate an ice age, atmospheric carbon dioxide must fall under 280 parts per million. Over the past 10,000 years, levels teetered at that brink. The globe stood ready. The gateway to glaciation was creaking open. But then we ignited the fuels. We drove the figure beyond 280, then 300, then 350. Now we're surpassing 420 parts per million. We've gone beyond tweaking the dial. We've demolished it. The buildup of greenhouse gases in our air exceeds anything seen in at least 3 million years. We've forged an atmosphere reminiscent of the Pliocene period, when the Americas remained separate land masses and forests, sprouted close to the Antarctic Circle. This thick carbon blanket functions like a barrier. It captures the feeble summer rays, holds onto the warmth, and won't release it. It utterly nullifies the orbital chill directive. Jupiter's pull keeps at it. The tilt continues its shift, but it counts for nothing now. Our emissions have overwhelmed the message with static. Humanity has achieved what no other life form ever has. We've canceled an ice age. This isn't poetic license. Considering just the orbital rhythms, Earth ought to commence its gradual slide into the next glacial maximum sometime in the coming 1,500 years. The ice caps should already be building momentum today, but due to the carbon we've released so far, that destiny has vanished. The impending ice age is delayed, maybe by 50,000 years or even 100,000. Certain projections indicate that exhausting all leftover fossil fuels wouldn't merely delay the frost, it could terminate the pattern altogether. We might drive the planet into such intense heat that Greenland's and Antarctica's ice masses disintegrate entirely, stripping away the reflectors from the system permanently. We've stepped into a fresh geological chapter. The Holocene has concluded. We're inhabiting the Anthropocene now. This era's ruling force isn't eruptions from volcanoes, nor cosmic impacts, nor celestial paths. It's humanity. We've taken command of the global engine. We've frozen the timer, yet we don't completely grasp the craft we're piloting. And we've floored the throttle. In doing so, we've secured an extended warm season. Yet the core issue lingers. What fate awaits a world engineered for icy epochs when it's compelled to scorch instead? We've secured a temporary escape this extended warm season. At first glance, it appears as a grand achievement. Our kind thrives in tropical climes, having originated amid Africa's balmy expanses. Lacking thick coats or insulating fat, we loathe the chill, halting the advance of glaciers and sparing our northern settlements from the relentless press of ice. Seems like the pinnacle of human ingenuity triumphing over the forces of the earth. However, this success masks a perilous deception. We've done more than halt the swing. We've severed the very line that drove it. Without that rhythmic driver, the globe doesn't settle into equilibrium. It spirals into disorder. By elevating carbon dioxide concentrations past levels unseen in the past 3 million years, we're guiding our planetary craft into what experts term hothouse Earth. Here, those feedback mechanisms we explored, the reflective surfaces and the pilfering elements, start operating backward. With Arctic temperatures rising, the pale ice dissolves, exposing the shadowy, insatiable sea below. That inky expanse soaks up additional warmth, accelerating further ice loss. The reflective shield fractures. Meanwhile, as the permafrost across the frigid northern realms defrosts, it unleashes ancient carbon trapped in icy soil for thousands of years. The pilferer restores its pilfered bounty. The earth now boosts the blaze with the same fervor it once intensified the freeze. Should this trend persist, we're not heading toward a steady, temperate Holocene. We're courting a revival of the Eocene. Picture mere centuries or millennia ahead. A landscape stripped bare of polar ice sheets. Antarctica transforms from a frozen wasteland into verdant terrain. Shores along the Southern Ocean sprout beach and fern woodlands, echoing conditions from 50 million years back. The Arctic turns into a lukewarm, marshy basin brimming with seaweed and plankton. In such a realm, ocean levels don't rise by mere inches. They surge 70 meters above current marks. Contemporary shorelines from Florida to Bangladesh, the Netherlands, and vast deltas vanish beneath the swelling azure tide. Yet the real toll of this prolonged warmth transcends rising temperatures or flooding. It's the erasure of the natural cadence. Those Milankovitch cycles, harsh as they were, offered a blueprint, a reliable pattern of flux and constancy. Ecosystems followed its guidelines. Woodlands shifted latitudes with the seasons. Wildlife adjusted accordingly. In hothouse Earth, that blueprint incinerates. Climate turns savage and capricious, powered by the colossal heat stored in the air. Tempests swell to global proportions. Arid spells embed themselves across land masses. The mighty ocean streams, the thermal highways circulating warmth worldwide, could grind to a halt or shift direction. We've swapped the steady, cyclical pulse of the celestial timepiece for the erratic, frenzied convulsions of a malfunctioning apparatus. Still the planet endures. The stone, the seas, the skies remain enduring. The carbon surge we've unleashed is enormous, yet limited. Fossil reserves will deplete. The surge will subside, and then geology's profound gradual mechanisms will initiate restoration. This demands vast stretches. 10,000 years, 50,000, maybe even 100,000. Mountain silicates gradually erode, binding with CO2 in precipitation to cleanse the atmosphere, bit by bit. Funneling the element oceanward for entombment in limestone, the delirium will lift, the air will clear, and once the carbon dissipates entirely, the underlying rhythm persists. Jupiter's gravitational tug endures. The planet's tilt continues. Solar rays keep bathing the high Arctic. The Milankovitch cycles haven't vanished. They're simply paused. They form the steadfast pulse of our solar realm, biding time until the clamor of the Anthropocene diminishes, allowing them to reclaim their role. Glaciers will reclaim their domain. It might span 500,000 years, but those colossal frozen behemoths will stride forth once more. For Earth isn't a lifeless hunk, it's a dynamic, respiring entity, and we're merely a fleeting delirium in its ancient, profound slumber. Now let's withdraw, abandon the planet's crust, ascend beyond the Anthropocene's haze, past the dissolving glaciers, clear of our society's din. Venture into space's serene void, to a vantage where Earth appears as a fragile orb of azure and ivory adrift in nothingness, and accelerate the clock. Viewing the past 1,000,000 years in fast forward wouldn't reveal a mere stone or fixed chart. It would unveil a vital being. We'd witness the North Pole's immense icy dome expanding, surging southward like overflowing cream, engulfing Canada, entombing Europe, blanketing the world in frost. Then it retreats, withdrawing to oceanic confines, uncovering the verdant and earthen hues of continents. Expand and retreat, expand and retreat. This pattern repeats in a steady cycle, every 100,000 years. It resembles the steady rise and fall of a chest. It mirrors a lung drawing in air and letting it out. The ice ages aren't some illness. They're no error. They're the very breathing of our world. Over the past 1,000,000 years, our planet has been inhaling. It takes in the chill and releases the heat. It pulls the seas onto continents as frozen sheets, then lets them flow back as liquid. This cadence forms the heartbeat of the solar system. It's Jupiter's gravitational pull, altering our path. It's the tilt of our axis, shifting toward the sun. It's the quiet, gleaming mechanisms of the universe, powering the rhythm of our sphere. And we are the beings born from that outward breath. We've raised our urban centers, recorded our pasts, and spent all of human history in this fleeting spell of mildness between inhalations. We're the offspring of this warm interval. We take the warmth for granted as endless, just because our own spans are so brief. Yet the planet follows its own vast timeline. It doesn't track days, ages, or empires. It gauges existence through loops, tilts, and revolutions. The quiet of the Earth isn't void, it's endurance. It's the endurance of a peak awaiting the glaciers to reshape it into powder. It's the endurance of the seas poised to swallow coastlines once more. It's the endurance of a world that calculates with precise math the inevitability of another freeze. The carbon we've released into the atmosphere is an interruption. It's a spike in temperature, yet fleeting. The stones will soak it up. The waters will conceal it. In time, the heat will subside, and even then the immense wheels above will keep rotating. The tilt will continue nudging the constellations. The path will keep elongating into the void. The pattern will persist, and the Earth, gradually and calmly, will start to draw breath anew. So, as you rest this evening, secure in the glow of this extended, lovely thaw, recall that cadence. Tune into the hush. It's not the hush of oblivion. It's the profound, unwavering, timeless respiration of the globe. Good night.